All right, thanks. Thanks for coming. So today I'm going to talk about this framework called Scio. It's a Scala API for Google Cloud Dataflow and Apache Beam. How many here use any type of cloud, AWS, Google Cloud? A lot of us. So yeah, all makes sense. So let's talk a little bit about us. I work for a company called Spotify. We do music streaming. We have a lot of features that the users seem to like music recommendation features like Discover Weekly. We actually also do a lot of big data for music labels or artist managers for label and user stream analytics. And we have a lot of users, about 100 million, in a lot of markets. And we have a fairly large Hadoop cluster, a 2,500 node. I think it's, as of today, probably 2,700 node, one of the largest in Europe, and we process a lot of data. So who am I? I've been at Spotify for a little bit more than 5 years. I started in the New York office when we launched in the US, and I did a little bit Hadoop before that, Yahoo search. We did spell check and search-related algorithms. So at Spotify, I mostly work on music recommendation and also data infrastructure. Actually, I'm pretty new to Scala because Spotify used to be a mostly Python shop, and we picked up Scala in 2013, mostly for data science. And that's when I started learning Scala and using it. So a little bit origin story. We used to do mostly Python. We had this framework called Luigi, which is a framework for both job scheduling and also Python streaming MapReduce. And it's been around for a really long time, and still there are a lot of companies using it. But it turns out writing MapReduce in Python is a pretty bad idea, especially if you're processing a lot of data, a lot of structured data in Avro or whatever schema data type you have. So around 2013, we picked up Scalding and moved a lot of our pipeline over. We also have people using Spark, mostly for machine learning use cases, and also Storm for real-time recommendation and ads targeting. So those are the type of use cases we do for data analytics at Spotify. And we have a lot of employees using Scala, about probably more than 130 developers writing data pipelines on a daily basis. And we have a lot of jobs, unique jobs. Earlier last year, we made this decision to move everything to the cloud. It's a big, giant leap of faith. At a point, we had maybe 6,000 machines, physical bare metal hardware machines. So it was getting to a point it's hard to scale. And Google, as we all know, is pretty good at scaling infrastructure, and they have a lot of pretty solid data infrastructure products. So we decided it's a good bet to move to Google and leverage their technology. So that goes to the question, what is Dataflow and Beam? We have to look at the evolution of Apache Beam from the very beginning. Around 2004, Google released this paper on MapReduce, which inspired a lot of open source technologies, like MapReduce became Hadoop. There's also Colossus, which inspired HDFS. Of course, Bigtable, which inspired Cassandra and HBase. And around maybe 2-3 years ago, they published a couple of more papers on Flume, which is a higher level data pipelining framework, and also Millwell, which unifies stream and batch processing. So the idea is that batch is really just a special case of streaming, and you can do both of them in the same unified API. They open sourced Dataflow SDK, and is a part of their Google Cloud products, and also later donated to Apache, which became Beam. So what is Beam exactly? Of course, it introduces the unified streaming and batch programming model. It also has this concept of SDKs, which the developer used to write data pipelines. Right now, there are 2 SDKs, Python and Java. There are other languages being proposed. And then your the pipeline that you write in a Java or Python SDK gets translated to one of the many runners supported. Right now, there are 3 Flink Apache Flink, Apache Spark, and Google Cloud Dataflow. There's also Apache Apex and Gear Pump under review right now. I think there are a couple of more runners being contributed to Beam as we speak. There's obviously also a local runner for testing and also running jobs on a single laptop. So Beam also tried to answer or ask the 4 important questions about data processing and streaming. So what is the computation you want to perform on your dataset? Flat map, map filter, group by, whatever. Where is your event generated in the timeline? That's usually the timestamp of your log message, obviously. When in processing time are you computing these results? In batch, that doesn't really matter because we just wait until everything is ready and then start processing. In streaming, it's more of an important question because we usually want to process data as soon as they arrive, but there's also always the possibility of losing data or dropping late data. And how asks, how do we deal with those cases? So there's a simple way to visualize these 4 questions. In batch, you just process everything all at once. In this case, probably a sum of numbers. In the window batch mode, you bucket your data into obviously hourly or minute windows, and then you process them one at a time. But then there's the question of streaming. In this case, we have a red event there that's arriving late, and in this case, we're dropping it. So the event time and processing time is not always in sync. And the last question, how do we deal with those cases? You can either accumulate, update, or maybe drop late data. So those are the 4 important questions about unified batch and streaming model. So this is the Apache Beam Vision. Obviously, the users can write pipelines in any language they prefer, which gets translated to any runner that's supported, and then it should run on any of these platforms. That's an ideal situation, but we are not quite there yet. And then I bet a lot of us here have used Scalding or Spark, so it's probably easy to compare the data model of Beam versus Spark. So in Spark, we have this batch mode, which and the abstract data type is RDD or resilient distributed data set. And there's also a dstream data type for Spark streaming. And really, it's just a sequence of mini batches or mini RDDs. So you end up with 2 sets of APIs for batch and streaming. Apache Spark also has this explicit caching mechanism, which is useful if you do a lot of iterative machine learning algorithms, but could also potentially cause problems because you have to deal with memory, like Java GC problems. Beam has a much more simplified data model. There's only one abstract data type called P collection, which handles both streaming and batch. Obviously, then you end up with one single API. You can write it once, and it should work in both modes. Elements in the P collection have timestamps, implicit timestamps, and also window assignments. So if you're consuming from Kafka or PubSub, the producer might generate timestamp for these elements. If you're consuming from a text file, log messages, then you have to pass them yourself and assign the timestamp for the elements. Another big difference is execution. So in Spark, there's usually one master and a couple of executors. The master will dynamically send messages to the executors through control plane, like serialized functions, to perform transformations. So like if you do rdd.map, that's a transformation. Sometimes you want to get data back from your RDD, and that's called action in Spark. So basically that triggers a computation and fetch data from the distributed memory cache in all these workers back to the master. Dataflow, on the other hand, has no master, so you basically write your pipeline. It statically generates a DAG, a graph for your computation, and the only thing you can do is transform. Then you submit your job, which executes in the cloud. You're completely detached from the cluster. Once you can only get your data back once the computation is done. So there's no concept of actions. As you can see, these two function signature. Come by value in Spark is action. It returns the in-memory map. count by value in Scio, on the other hand, is a transformation. So it transforms one S collection into another S collection. So why do we use it? I mean, there must be some reason, right? So compared to the other options we have before Dataflow, we still do that. We still use Scalding a lot in the company. You can run it on the Google Cloud as well. Obviously, the advantage is very mature and reliable. There are a lot of companies using it. It runs on Hadoop, which is also proven. The downside, obviously, you have to manage a Hadoop cluster, and it's not an easy job managing like 2,000 plus node cluster. You have the problem with multi-tenancy of resource sharing and utilization. There's no streaming mode in Scalding. Obviously, you can use Hummingbird, which runs both on Scalding and Storm, but that adds more complexity, right? You have to maintain two separate clusters. There's also no integration with the rest of the GCP ecosystem, like BigQuery, Bigtable, or these Google Cloud products that we want to move over to. Spark has a similar situation. Spark has more features. It supports batch streaming, SQL ML, a lot of different languages. It has web UIs like Zeppelin and Spark Notebook. The downside, again, is cluster management or operations. We have a lot of data scientists who are not engineers, and it's very hard to expect them to spin up and tear down clusters using a lot of scripts and then do a lot of tunings by hand. So that's a problem, especially if you run a large ML job that has a lot of in-memory caching. That's where a lot of these reliability problems pop up. You have workers dying due to GC timeouts and failures and triggers recomputation of the entire DAG. So those are problems we've seen. And the last problem is also ecosystem. There's no integration with the Google products, so it's hard to integrate. So that's why we picked Dataflow and then use it with Scala. Obviously, Dataflow comes with a Java API. It's a fully hosted and managed service, which means you write your code in your local IntelliJ or Scala repo, and then you submit the job. It spins up a cluster in the cloud automatically, fully managed. It handles like things like auto scaling, sharding, and then it comes with adapters for all the Google Cloud infrastructure products. Also, another selling point is unified batch and streaming model. And by the way, for those of you who tried Flink, the Flink streaming batch unified model is also inspired by the same Millwall book that Dataflow is based on. Obviously, you're here, so you like Scala. Obviously, we want to write Scala instead of Java. Functional programming is a good fit for data processing. And we use a lot of Scala libraries for doing numerical and statistical computation as well, like Breeze, which is like NumPy for Scala, and also algbird for a lot of the parallel approximation computation. So this is what it looks like. Basically, we took the Java SDK and all the goodness from the Google Cloud and put a bunch of Scala API and wrappers and utilities on top, and to make our life easier. So the name Scio, it's pronounced Scio. It's ecclesiastical Latin, which is the type that the Pope speaks. That's what I'm told. So pretty classy. It's a library for Scala data framework that starts with SC and ends with IO, and buzzword compliant. Unfortunately, I couldn't register the SC.io domain name for whatever reason. Anyway, it's public on GitHub under Apache license 2.0, so check it out. A couple of companies using it already, and so far they seem to like it. This is what WordCount looks like in Scio. The API is heavily inspired by both Scalding and Spark. Basically, we took the bits that most of our users like from the two different frameworks and put them together. And it's probably 80% copy pastable from Spark. So another bonus point. It's a very easy transition for a lot of our users. And of course, PageRank. 10 iterations of PageRank. You have an input collection of tuple 2, source and destination strings. You map out the links and initialize the rank at 1.0, then over 10 iterations redistribute the rank, and then you apply a damping factor of 0.85. So that's page rank in a couple of lines of code. So that's what Scala people like, and easy to write pipelines, easy to reason about. So why do we like it? There are a couple of features that our users seem to like a lot. Type-safe BigQuery. BigQuery is the Google Scio big data analytics engine, which can process like terabytes of data in a matter of seconds. BigQuery is actually based on the Google internal technology called REPL, which is also the same paper that inspired Apache Parquet, so columnar storage, column projection, predicate, push down, those kind of ideas. They all came from the REPL paper. The Google BigQuery API gives you rows in the form of table row, a type called table row, which is really just a JSON type. It's a map, glorified map of string to objects, so it's hard to work with. In this case, we just built some macros to generate, because you're performing the query, so you already know what the return type result schema is. So we just generated case classes and converters from the query at compile time. And you get case classes, which is type safe, and it just removes a lot of the boilerplate null point exceptions and just guessing and retrying, those kind of pain when dealing with untyped data. We also built a repo, which is, again, inspired by Spark. You can interactively pull data from the Google Cloud, from cloud storage, Bigtable, or BigQuery in real time. I'm going to give it a demo in a couple of minutes, but it's just a single jar. There's no installation. You download it, you run it, and then use your default credential. Again, because as I said earlier, there's no cluster management in Dataflow, so you don't have to spin up a cluster and run the REPL or driver over there. You just run a jar locally and talks to the Google Cloud Service. And in Spark, if you save something to disk, the save method, save as text file or whatever, they return unit because that's the end of your pipeline. You're done. You're saving data to disk, and there's no more processing afterwards. But in Scio, we added this future-based abstraction, so they actually return a future which will be completed once your data pipeline is executed and completes. And then we can use that to orchestrate like multiple pipelines. And is this example, you have a future from a first pipeline job, close it, then you reopen the return future in the second pipeline. Distribute cache, so there's a common Hadoop pattern, and we just re-implement it in Dataflow. Because we have access to the cloud storage or HDFS, we can just pull files to workers and load them into memory in whichever form we like. And we do that quite often with like binary tree lookup trees or hash table like lookup tables. And a couple of other goodies. Obviously, Dataflow has a web UI, and then we mapped the Scala function names, source code file, and line number to the web UI, so it's easy to visualize. We added a bunch of goodies for BigQuery and HDFS source and sink, which means you can run your Dataflow job in the cloud, but also read and write your on-premise or your Hadoop cluster in the cloud. And enhancement for like metrics and Bigtable. So these are the other stuff we added on top of the Java SDK. All right, so let's try the demo. Can you guys still hear me? I have to turn off the mic. Anyway, let's try this. So I just installed the Java via Homebrew. It's already there. You run a command. Is the text big enough? Yes. All right, so I have a console. It runs on my local laptop, but I picked up my Google Cloud credentials. Also comes with a BigQuery client, so I can do things like get table rows. Give me rows from BigQuery table. This is track entity. That's all right. Okay, thank you. So I have a BigQuery client. I want to get rows from BigQuery table. This is the native client. So I'm doing this. This is a really fat table. This table has maybe a couple hundred columns that contains all the metadata about our Spotify catalog. This is actually real live production data. Let's see. All right, I get an iterator of my data. So .next. This is the untyped JSON you get from BigQuery, which is kind of annoying to work with. Obviously, you refer to columns as using strings, and you get an object back. Obviously, and also I can't type, so you get null. It should be master metadata. All right. Now you get an object. Then you cast it to something that you think it is. Table row. I've done this like a million times, but whatever. Now you get a nested record. Then I do that again. Track. See, it can be very annoying. Imagine running a pipeline and 2 hours later, it MPE somewhere deep inside the code. So let's try it again, but using a different approach. I have this snippet, copy. So this is just an annotation, BigQuery type. Say, give me a type from a query. This is my query, selecting all these columns. The system already knows what columns I'm requesting from BigQuery, so it can do a dry run and figure out the result schema. And I have a class, but I don't have to write any code for it, because why should I? It generates classes. And now I have this track entity class. It's just two pretty string, print it out. You have fields with typed option for nullable fields. And let me get BigQuery.get typed rows back. Track entity, I want to get my data in the form of track entity. I don't need to re-enter the query again because it's already embedded in the type. T. This data set is about 400 gig, I think, contains 70 million rows. That's the number of tracks inside Spotify. And it should take a couple of seconds. Done. 10 seconds. All right, so I get a new iterator. Next. Track entity, that's a case class. So audio attributes. Okay, that's option. But since I know it's a sum, I just get it. And tempo. Yeah, so that's how it works. Can easily pull data from BigQuery live, and let's run a job again. So I started this repo without any parameter. So by default, it will run everything locally. So let's run a word count. Text file. So I already have this in my history. So basically, what I'm doing is read this text file from the Google Cloud storage, flat map, split, to lowercase, come back value and materialize, which will give me a future. At this point, the pipeline is not evaluated yet. When I close my pipeline, context, submits the job to the Google Cloud. Actually, this is running locally, so it's not submitting it. It just pulls data live from the cloud and does the computation locally on my laptop. So don't do it with large data set. You'll blow up the JVM heap. All right. This usually takes like a second or two at work. I blame the network here, but get my result back. So remember, I have a future, and this is already completed. So I can do future wait for result dot value, which is the value inside my future, the abstraction. It's an iterator. Take 10 of them to list. That's my word count. What if I realize this is too big? I have to run it in the cloud. So I can do something like this. Say, reconfig my options with this Google Cloud project, some staging location, some bucket in the cloud, and run with a real Dataflow pipeline runner instead of the local runner. So I do that. And give me a new context. So if you've done Spark, each Spark context or repo is basically connected to a single cluster, and you can't do it live because then you have to tear down or expand or shrink the cluster. But in this case, I can do that. So I'm saying instead of doing that same code locally, I'm just gonna copy paste same piece of code again. And now instead of running locally, it will submit the job to the cloud. It actually builds the job locally and then submit the job to the cloud and gives me a link, a tracking URL, so to speak, and I can see it. So it starts running. We can take a look again. It should take maybe 2 or 3 minutes. But let's go back to the slides. Thank you. Yeah. So who's using it? It's Spotify. There are actually a lot of teams using it already. Most of them are new to Scala or Scio. Actually, a lot of them are just business analysts or data scientists who doesn't code as much, or used to Python and R, but it's fairly easy to pick up. We also try to adopt this open source by default model now that we're on the cloud, so everything's open on GitHub. We have our own Slack channel internally for answering questions, but we have open Gitter and mailing list. So if you find some issue or have any discussion questions, feel free to file them on GitHub or join the discussion. And a lot of the features are actually driven by both internal and external users, so they contributed a lot of the patches and feature enhancements to like the following components. Release radar is one of the latest features that we released. It's a personalized new release recommendation. Like, every Friday it gives you a playlist of all the new latest albums or tracks that you might like. This runs on 50 N1 standard 1 workers, which is 1 core and 4 gigs of memory, fairly small, and consumes like 130 gig data, and then ingest them into 2 Bigtable clusters. We have one in Europe and one in the US. There's a lot of Bigtable mutations, 110 million, like one for each user. The entire code is 120 lines of code. Yeah, that's the entire job. Fan insights, that's the content creator face inside of the business. So like if you're a label manager, if you're an artist, you want to see who's listening to my tracks from where. We do a lot of slicing and dicing over many dimensions, like track, artist, over different play contexts, like from a playlist, radio, or recommendation, geographical, demographical dimensions, and over daily, monthly, weekly aggregation. This processes like terabytes of job on a daily basis. It used to be 150 Java MapReduce jobs. Now it's less than 10 Scio jobs because you can just do so much more in a single Scala pipeline. And yeah, master metadata, that's the metadata I was using in my demo. That actually uses auto scaling, so the job might use from 2 to 35 workers at any time based on throughput. It joins 26 datasets from content providers, SQL dumps, XML dumps, and a lot of different sources. 70 million records, 120 gigs of data. The code is 200 lines of code, yeah. And it was ported from Java, so the original code was 600 or more. This is what the pipeline looks like in that web UI. This is massive, but it's actually very easy to write in Scala. So this is like the number of inputs and the joins and group bys and slice and dice happening inside the pipeline. Another little utility that we built to make people's life easier, it's called BigTV. You all know what diff does, diff into text files or any kind of files, but we want to diff datasets. So this is what I call pairwise field level statistical diff. So you take 2 datasets, give it a key function. Now you can have pairs of records from left-hand side and right-hand side. The records can be Avril, BigQuery, Protobuf, whatever. And then it drills down into the fields. So it computes like a delta. It could be numerical, it's just the difference between the 2 values. For string, it could be edit distance, but you can override it. We use vectors a lot, like latent vectors from machine learning. So in that case, it can be a cosine similarity or distance. And now that you have a field level delta of each pair of records. You can compute it on a global level, the global statistics, min, max, average, and also standard deviation, those kind of things. And a lot of the time, there are like non-deterministic fields in your data, like timestamps or hash code or whatever. You can just ignore them or specify fields to ignore. And also, sometimes people use list of strings or list of items as a set. In our case, sometimes a list of the countries the track is available. You can specify that field is unsorted, so we will ignore ordering when comparing the diff. You get statistics, obviously, the number of records or pairs are the same, different, missing left or right hand side. We use that to validate pipeline migration. Imagine if you have a Python MapReduce streaming job and you want to rewrite it in Scio, and then you want to validate that it works exactly the same way. Obviously, people don't write tests when they write jobs in Python. Then we have to figure out, is this doing something sane, and just diff the result of the two pipelines. And we can use that for sanity checking machine learning models, like you tune a parameter, how different is my outcome? Is it statistically significant or not? You have all these stats that you can use to compute it. The code, you take the left-hand side, right-hand side, key on the function, do Autojoin. Now you have a key and then two options for the left-hand side and right-hand side value. And if both of them are present, you do your delta, then you end up with the output tuple. That's the key, the primary key of your data set, the delta, the list of field deltas, and also the delta type. The second step is we map this thing into a map where the key of the map is your field name. It's like track ID or user age or whatever. And then the value is just a tuple of all these different things. But notice that all these things are actually summable or have semi-groups defined on them. So if you, the first line of this snippet is algebra, and we use algebra heavily. So we map everything into a tuple of semi-group summable types. And then the actual computation is the last line. It's that, just sum. When you do that, it summons a semi-group over this map type, the map of string to the tuple, and then recursively summons semi-groups for every individual columns, individual fields in the tuple 2 here. Yes, so that's how it works. Other uses, we use it for a lot of other things as well, A/B testing, monetization, user understanding, ranking, all sorts of things. Finally, let's talk about Scala or how it works. A few interesting lessons learned. Serialization, it's the hardest part in big data. There are two types of serializations happening in the pipeline. You have to serialize your data. A lot of the common Scala libraries, Scalding, Sparkstorm, they all use Cryo and Geo under the hood. So Cryo basically does reflection and a lot of bytecode manipulation to figure out how to serialize your records or objects. And Geo is a Twitter library that implements a lot of the serializers for Scala types. Dataflow requires the explicit coder implementation, which means you have to implement your own for every new data type that you define. That's annoying. And because it's in Java, they sort of abuse a lot of the Java type system to make that happen. In Scala, we have class tag, so you can do runtime reflection to figure out what's in my pipeline and what's the best coder for that. So that's data serialization. And the next problem is lambda serialization, which is way harder. And lambda is only serializable with Java serialization, not any of the libraries that's available out there, so that's annoying. And your lambda might pull in a closure that has fields or members that's not serializable. We use the closure cleaner from Scio to basically at runtime nulling fields out to make them or force them serializable. And obviously you can use the other tricks like making things serializable until they work, and marking fields as transient lazy val until they work. So those are the type of tricks we have to do to make sure the pipeline is runnable in the cloud. Whoops. Repo, another pretty challenging topic. In Spark, the repo actually transports your Lambda bytecode from the master node to all the workers. And there's a little HTTP service on the workers to download them. Dataflow, as I mentioned earlier, it's a static execution model, so you have to have a jar available while submitting the job. And once you submit the jar to the cloud, it's over. Like there's no communication between the local node and the cloud. So basically what we did was we hacked the Repo, have our own custom class loader and iLoop, and then intercept the compiled bytecode, put them in the job jar, and submit it. And the guy who wrote it used to manage the Hadoop cluster at Spotify, so his previous job was to restart the name node like every other day, middle of the night. But since now we don't have to operate our own cluster, he did all this cool stuff. He's actually over there somewhere, Rav, yeah. All right. And macros in IntelliJ are another challenging problem. So if you guys ever use things like shapeless or simulacrum or some other Scala libraries that generate code at compile time, some of them are not, or most of them are not picked up by IntelliJ. So you might see red underlying stuff in IntelliJ that's actually compilable in SPT. The problem is IntelliJ doesn't pick up macro generated code. And like in our case, the BigQuery case classes. So obviously the solution is to write your own SVD plugin. That seems like a mature thing that every tech company is doing these days. Just write your own SVD plugin. So we did that, and it picks up macro-generated case classes for IntelliJ. So now you can do like tab completion of your data type inside IntelliJ. Scio for Apache Zeppelin. Zeppelin is the web UI originally for Spark, but it also runs on a bunch of other big data frameworks, including Bigtable. So another nice thing about Scio or the Dataflow with Zeppelin is I demoed before in a command line repo. There's no cluster. You don't need to set up your cluster. So in this case, we can just distribute a runnable jar to the users. They can run everything on their laptop, and it only talks to or communicate to the cloud when you perform some real computation, like submitting a BigQuery or a jar. So that's another potential use case for this Zeppelin interpreter for Scio. Yeah. And a couple of other experimental features, playing around with shapeless, playing around with Protobuf. Some of our users prefer Protobuf over Avro. And if you've compared the two, there's no way to manipulate schemas in a generic way in Protobuf. So we kind of worked around it, and now you can deal with this sort of like Avro. So you have utilities that can inspect Protobuf serialized bytes and deserialize them into JSON and vice versa. So it's mostly for productivity rather than performance. So yeah, last thing, what's next? By default, Dataflow supports both streaming and batch, so Scio supports both also by default. The one constraint in Dataflow is that to update a pipeline, a running pipeline, all the transformation needs to have deterministic naming, which is not the case in Scala because we name them the functions and the file names in your source code for easy bug fixing or troubleshooting. So that's something we need to work on. Right now we have a working branch that runs Apache Beam 0.2.0, and then we're working on 3.0, the latest release. Obviously, it's tightly coupled with Dataflow right now, but it shouldn't be too hard to decouple those components and make sure it runs on, say, Flink or Spark as well. And the last thing, once Apache Beam stabilizes, it's our plan to donate it to Apache as part of the Beam Scala DSL. That's it. That's the end of my talk. So if you have any questions, we can do it offline. I think we're running out of time. Yeah, but that's it. Thank you.